Ah, okay, where were we? We had just talked about not leaking capabilities. And now I'm showing an example here. This is our old friend, the fool's assignment operation, where instead of doing a simple assignment, we destroy the object and create a new one with the new value. And we have now carefully put claims of destructibility explicitly in our interface. Implicit claims of proper are shown here with the blue dot, indicating that that is an implicit claim. And we return to our favorite question. What could possibly go wrong? Anyone have an idea?
The two parameters could alias the same object.
You got it. The two parameters could alias the same object. And in this case, we have destroyed the object before reading from it. And we have created undefined behavior in the implementation based on a danger in the calling neighborhood. And we want to figure out how to get these two, the fire into the same neighborhood as the danger. And this one's a little complicated because X was proper, Y was proper, X was destructible. But the danger came from the caller knowing that this thing was aliased and the implementation not knowing. That is, the implementation had some capabilities it received that interacted in a way that the implementation could not see. And this is a pretty big problem. Everybody runs into this sooner or later. And it's subtle. And people wonder, how should we tell when objects are aliased? And you could compare the addresses, and if you compare the addresses all the time, you can find out. But that gets really crazy because you have to do tons of address comparisons, and now you're looking at tons of cases, and you're making your code go slow, and that's just no fun at all. But the important question is not how should we know that things are aliased? Because remember, these capabilities, the proper of X and Y, the readable and writable, these trace back to the construction of the object. When the object was constructed, we knew what it was aliased to. It was aliased to itself and nothing else. So the point is not to figure out what's aliased, but to figure out how not to forget that things are aliased. Somewhere along the lines, in order to have this problem, we had to forget that things that we knew were aliased were aliased. And in this example, I've put it right here. Bar knows about the aliasing. Implementation of food does not know about the aliasing. We need to find a way to express that in the interface. So I'm going to make this definition. Two L values are irresponsibly aliased when the aliasing is not communicated across the interface. And there's some more detailed words about what happens on which execution path. But the important thing to know is irresponsibly aliased means one neighborhood knew about the aliasing, one neighborhood did not. And in particular, the responsible neighborhood knew about the aliasing, and the irresponsible neighborhood didn't. Yes?
What about internal members of structs?
The question is, what about internal members of structs? It is true that, that yes, in a sense, the internal member of a structure is aliased to the entire structure. And you can think of that as sort of a partial aliasing. But what I'm going to say is it's the internal member is aliased to itself. And if you want to express that aliasing, you are going to have to be able to talk about the internal member of the structure. So I'm going to actually slide this definition back into writable and readable. Here is the local non-aliasing version of writable. It has no effect when writable has been previously asserted in the responsible neighborhood more recently than the L value appears to have been destroyed. That is the old part. And the object is not irresponsibly alias to any L value that may be readable, writable, or destructible in an irresponsible neighborhood. And I know I'm just saying don't do the thing that I said was bad. But this is the point where you check. You want to check at the point where you need writability. Because if you don't check, then there might be some disagreement on how operations affect each other later. Before you assert writability, that writability is not going to affect any other operations. And before you assert readability, that readability is not going to affect other operations. And here's readable. Same thing, not irresponsibly aliased. A little bit off here, I'm not it's okay to alias. I say here that it's okay to alias readable to readable. That is the list in the second bullet point. Doesn't mention readability. There's a much more nuanced definition that really belongs here that didn't make it into the talk. And, well, there's paper. You can read the paper for the nuanced version. And similarly, destructible. Destructible has no effect when destructible has been previously asserted in the responsible neighborhood more recently than T appears to have been destroyed, and not irresponsibly aliased to anything that might be readable, writable, or destructible in an irresponsible neighborhood. So this irresponsible aliasing is an extra condition that we put on readable and writable and destructible when they appear in interfaces. Outside of interfaces, there's no irresponsible neighborhood. The extra condition can't happen. But if there's an irresponsible neighborhood, we have to make sure that the irresponsible neighborhood knows how the capabilities that we give it interact. So, all that talk has the effect of moving the fire to the second claim of propriety here. Here, the responsible neighborhood, the neighborhood of bar, the caller, says X is destructible. It says X is proper. So far, so good. And then it says Y is proper. And that's where you notice. But Y is irresponsibly aliased to X. So this makes it not okay for bar to call the function this way. This function does not allow aliasing. But what if we fix the function? Here. Now we have an implementation that can support aliased parameters. I read into a temporary and then created the object from the temporary. And now our interface is really stronger than we want. We want to allow aliasing in this interface. We need a syntax for that. I'll use this. Claim aliased X and Y. Now everybody knows X and Y refer to the same object. So, problem solved. We claim that X and Y are aliased, and there's no irresponsible aliasing, and we got our proof to go through because we used a temporary instead of going straight from Y. not a problem anymore. Yes?
Is that meant to say they have to be aliased or they can be aliased?
Yeah, that's the awkward part about it here. It says they have to be aliased. And maybe sometimes you didn't always want to do your fool's assignment from the object you started with.
It just seems to me that you turned this entire thing into a no-op.
Marshall says, I've turned this entire thing into a no-op, and he is pretty much right, you know. Yes. I've done a really crazy way of assigning a thing to itself, and there's really nothing else this function can do. But there is, with a different caller, you run into this problem. Here, this caller doesn't actually alias the parameters, and now the claim of aliasing fails. So it would be nice if we only claimed aliasing sometimes, when it's important. We can do this. And this works. If the addresses are equal, we will claim aliasing. If the addresses are not equal, we won't claim aliasing. And, you know, I put in a little graphic here. Look, no aliasing. Or change it the other way. Look, there's aliasing. And we get it right both ways. And this is actually really useful because it signals to the implementation neighborhood that the proof of correctness needs to be done in two cases. One case where the addresses are equal, one case where the addresses are not equal, and it works both ways. Proofs aren't hard. Mathematical notation is sometimes hard, but proofs are actually pretty easy. Yes?
So how do we handle overlapping values? Like on some architectures, it's impossible, but still get like two arrays, for example, or something like that.
Okay, the question is how to handle overlapping values. I think this feeds into the, like, what if one was a member of the other question too? You asked about arrays. But if I want to say that X is aliased to a member of Y, if Y was a structure, I would say claim aliased of X comma Y dot member. And if I wanted to compare the addresses, I would compare the address of X to the address of Y dot member. If I want to compare the addresses of 2 bytes in a byte array, I can do that. If I want to do something like memcopy is the one that doesn't... Memcopy allows one direction of aliasing, but not the others.
No, memcopy is behavior if they overlap. Memmove.
Both directions. Okay, memmove. Yes, memmove allows any sort of aliasing. I thought memcopy had one sort, but not the other. I don't know. But anyway, memmove is the safe one, allows aliasing. Does the right thing. Memmove can say in its interface, I'll loop over all the possible comparisons of the different ways the two arrays might overlap. And if the pointers line up in a particular way, the overlapping portion is aliased. So loops, great for these sorts of things. They go with your arrays. Any other questions? Okay. Okay, I'm going to switch to a more normal sort of assignment. I'm going to get rid of the destructible and reconstruct and just go to a simple assignment. But I will give it a more usual interface here. The more usual interface for assignment returns a reference to one of its parameters. And here we have improper aliasing again. Yes, every assignment operator has improper aliasing according to the basic interface, because it hands back both a result and a parameter. Both of them need to be proper, but the interface, the basic interface, doesn't say your result might be aliased to your parameter. Or at least, I haven't said it says that. So one way to solve this is we'll just put in the interface to our assignment operator, claim alias. This time, we don't need a conditional on this. Aliased every time here. And this is actually a really nice thing for a compiler to know about your assignment operator. And usually they don't if your assignment operator isn't inline. There's nothing that says you can't write an assignment operator that returns a reference to something else. And that matters to your compiler. So if compilers can rely on this, we can get a little optimization there. So that's one way to handle this. A different way would be to say that these rather complicated claims belong in the basic interface. That is, parameters might be aliased to each other, results might be aliased to parameters. And we can ask, do we want that as part of the basic interface? Is this the usual thing? There's a pro argument. You might have figured out by now that I give the argument I don't believe first. But the pro argument is more common functions would fit the basic interface, and some really important ones have aliasing built into the way we use them. Assignment operators, streaming operators, swap, all of these things we expect to work even when the parameters are aliased. Or with assignment operators, we expect the results to be aliased to the thing we pass in. Stream operators, we expect the result to be aliased to the thing we pass in. So this would make those things obey the basic interface. But I'm going to go with con because every if statement makes your proof break into cases. And having a lot of cases in your proof makes it really hard to get the proof right, and it makes it harder to check the proof too. Also, assignment, stream operators, and swap don't really want to have the basic interface. Assignment wants to have an interface that says you actually did an assignment. That is, that the result has the same value as the thing you passed in. Swap wants to have an interface that says these two things are the same things in the other order. And the stream operators want to have an interface that it's not aliased, it's not maybe aliased to the same stream. The stream operator wants to have an interface that says it's definitely the result is definitely aliased to the same stream. So the basic interface is not the interface that fits everything. It's the interface that you start with as a blank page and build things up from, and it's the interface that fits a fair number of things. So, how much time do we have? 30? Ooh. This went so much faster than last time. So I'm actually going... We get bonus slides. If I can figure out how to show the bonus slides. Do you know?
No, I had a question about the previous slide. I've been wondering why you don't reclaim the alias of X and Y in the epilogue.
Okay, I will.
You can't really change it, but everything else that you've claimed in the prologue, you've re-preserved in the epilogue.
1 second. We were here. This is the one you're,
Yeah.
so, can you repeat the question?
So everyone else reclaimed something in the prologue, we generally reclaimed it in the epilogue. You don't reclaim alias of X and Y if outside of X and Y in the epilogue.
Yes, the question is, everywhere I've claimed something in the prologue, I reclaim it in the epilogue, and here I don't reclaim it in the epilogue. And the question is why? That is an excellent question. I'm not sure I really understand the answer. And perhaps I should. But I will say aliased is different from the capabilities in that we're talking about things occupying, two capabilities basically occupying the same space is what aliasing is about. And that's something that can't actually change during the lifetime of the capability. But so I think I will go with the basic answer of maybe I should, but I don't really understand aliased well enough to be sure. Aliased is kind of complicated. So there and there. Now we can have a little bit of more interesting stuff. So here is a weird sort of function. It's not that weird. This is comparing two pointers to using studless instead of less than, because studless is the actual comparison for pointers that aren't related. If you can ask me afterwards about why that's important, but it's not important to the talk, but I didn't want to write obviously wrong code in the slides. I think this is a function that has the basic interface. Compare two pointers, produce the minimum, I believe. Yes. This minimum of 2 pointers, fairly straightforward, basic interface. Here is a similar function that's a little wackier. Going to pass in two references. I'm going to compare them to see which one is at the smaller address, and I'm going to return the value that was at the smaller address. And if this makes you a little nervous, I think that you are an ordinary sort of programmer, because this should make you kind of nervous. And in particular, if you had code that did this, that made copies of its parameters and called foo twice, you might not get the same result because the copies were in different memory locations than the originals. And that's a really weird function. Rudyard Kipling wrote a story about the cat who walked by himself. All places were alike to him. This function is not a cat who walks by itself. This implementation treats different places differently. All places are not alike to it. And that's actually something we want to avoid. A good function is a cat who walks by himself. The question is, just what is wrong with that weird comparison there? And I'm going to say that an R-value expression is indiscernible to a function if the function is symmetric with respect to permutations of the possible values of the expression. That's a weird sort of word, indiscernible. it's all places being alike. Places are indiscernible to the cat who walks by himself. And so most functions, if you take the address, if they take the address of the parameter, they expect it's an address. They're able to take the address of the parameter, but they're going to treat every address like every other address. They can see that there are different numbers, but it makes no difference to the function. And that is what's wrong with this function. This function takes the address of its parameters, and its result depends on just what the addresses were in this unexpected way. Now, the function that compared pointers was very similar to this. It had two addresses, it compared them, but what was different about the addresses in that function versus this one? The difference is these addresses have capabilities associated with them. These addresses, there's a proper object. And it seems that if you have a proper object, you shouldn't care where it is. If you care where it is, you care about the address, you shouldn't be looking at its bits. If you don't care where it is, you can look at its bits. It's this kind of trade-off. And you get this trade-off in a whole bunch of places in the language. So the addresses of readable, writable, destructible, or proper L values should be locally indiscernible. You shouldn't care what the addresses of the things you write to are, or read from, or destroy, or are proper. So I think the answer is that those functions should tell us, okay, we gave you a capability, but we've taken away the discernibility of the address. There's something similar if I say that a range of things is proper. This, for example, would be happening in for a vector. I pass you a vector, I say, this range of elements is going to be proper. Well, it's not just the addresses of those elements, it's also the end pointer needs to be taken away. It's indiscernible too. If I dereference an iterator, that means I care about the thing pointed to, not about the address. Generally, I'm not quite sure. This is weird stuff. I haven't really figured it out. The representation bytes of a scalar object, if I give you an int and say it's an int, what I'm saying is I don't care about the individual bytes. I care about what number it represents. The padding bytes of a plain old data object, similarly. If I pass you an object, I pass you a structure, you can read the padding bytes. They have to be initialized because you have to be able to do a byte-wise copy of it. But it's important that whatever you do doesn't actually depend on the values of the padding bytes. Your input is the same even if the padding bytes are different. Yes?
So you're not mentioning padding bytes for non-pod structs. I mean, I get that you don't, because you don't have to do byte-wise comparisons, their values are not important, but they're still here that you want to not deal with.
So the question is, or the statement is, I'm not mentioning the padding bytes for non-pod objects. And I could, you shouldn't depend on the value, but it's not actually clear that when I say an object is proper, if it's not a pod, I'm probably not saying that its padding bytes are readable or writable. So if they're not even readable, then they're probably not discernible. So I think it's fair to say that padding bytes for non-pod objects or the vtable pointer, those things are not readable and writable. But for pod objects, you have to have readable and writable in order to do byte-wise copying. If it's non-const, you have to be able to copy into it, and so you need writable. Marshall's confused, I think.
I'm just pondering.
Okay.
I'm pondering the difference between member-wise assignment and
Okay, I'm going to move on while Marshall ponders. And I'm going to say, back to our implementation gap. Here's an extra thing I will throw in. In the implementation, this is not an extra thing, this is an old thing. In the implementation, we know anything locally readable may be read. And only those things. So that actually tells us the complete input to the function. If it only reads from the things that we say are locally readable, we can say its gross input is the R values and addresses that it has access to through those capabilities. So here is the total, the gross input, not even total, gross, because it's too big. This is the gross input to the function. It has the addresses of the parameters, it has every R value mentioned in the prologue, and everything that could possibly be read using the readability from the prologue. It gets all that stuff it could use as input. But that's too much. Similarly, the gross output, we can say, is all the stuff in the epilogue. Anything that the epilogue says is readable is part of the output. Plus, address of the result, part of the gross output. What we could say, if we were Platonists, and maybe some of you are still Platonists, we could say that the net input is the gross input modulo indiscernible changes. That is, the net input is your structure minus the fact that Boolean has modulo the fact that Boolean has 10 representations on your architecture, or modulo the fact that the padding bytes might change, or modulo the fact that the address doesn't really matter. All of those things that are indiscernible don't matter to the net input. And similarly, all those things that are indiscernible don't matter to the net output. This, however, is a kind of Platonic definition. That modulo has to happen in the Platonic universe. So instead, I'm going to draw a commutative diagram and say the mapping that if you have a gross input and you make an indiscernible transformation to a gross input of another function call of the same function, and you apply the two functions, then there will be an indiscernible transformation of the gross output of one to the gross output of the other. And that's a way of saying it without that whole modulo thing, and mathematically a little more solid, a little more category theory. I think I'm not getting a lot of response here. So
Well, just trying to understand the graph. Does the dotted line mean that it's not the same transformation?
Does the dotted line mean it's not the same transformation? No, that's this is actually the way it's category theoretic habit. So the dotted line means if you have the first three arrows, if you have the solid arrows, then you get the dotted arrow for free. So if you have the three solid arrows, there exists a dotted arrow.
Right. What can we say about it though, with respect to the
What can we say about it? We can say that word indiscernible about it. That is, the difference between the gross outputs will be these changes that shouldn't matter. So if I call the same function twice with indiscernible inputs, that is, if the differences between the inputs don't matter, then I will get results that are indiscernible. Not the same. They might be stored at different addresses, they might have different padding bytes, they might have different internal representation that we don't care about, any of that stuff. They won't be the same, but they will be indiscernible. They will be enough alike that we don't care they're not the same. And this really is the procedural programmer's answer to the idea of what's a pure function. It's, can you repeat, we think we learn functions with like plus, and you add 2 and 2, you get 4. You add 2 and 2 again, you get 4. You get the same answer every time. And that's the thing about functions. But functions in C++ are not functions in mathematics. Functions in C++ are algorithms. And when we add, 2 complex numbers, we get a new complex number in C++. And if we add those same numbers again, but maybe we stored them in different addresses, we want to say we get the same answer, but maybe the answer is stored in a different address than the first one too. So what I'm saying is, if we repeat the function call by using indiscernibly changed inputs, we get indiscernibly changed outputs. And here is that rule. And R value is irresponsibly indiscernible when local indiscernibility is not communicated on return from implementation to caller. Now this is kind of turned around the other way. I'm not saying if the inputs are indiscernible, then the outputs are indiscernible. I'm saying that if the outputs, what am I saying? Trying to wrap the words around this one. What I'm saying is, if an indiscernible change in the input could have led to different outputs, you'd better say that that difference didn't matter. So, we can always get to this point, because all we have to do is say that enough stuff doesn't matter in the epilogue, and then we can say there are indiscernible changes in the epilogue. So really the error doesn't come from not being repeatable. The error, in a certain sense, comes from not having a wide enough definition of what repetition is. And now I want to get back to our example. So here, we're going to fail the implicit claim of no irresponsible indiscernibility that I'm going to put at the end of the normal epilogue, not the exceptional epilogue of a function. That is, if you return from a function, everything about your epilogue that didn't depend on, that wasn't controlled by discernible changes, by discernible aspects of your prologue, has to be marked indiscernible. And here, I have said that the result is proper. Therefore, the value of the result, that int, ought to be only dependent on discernible aspects of the input. And in this case, it's not, because we made a choice based on an indiscernible aspect of the input. Now, there is a way to fix that. We'll do this. We will put in our prologue this comparison. We'll calculate the comparison we're going to do. and say, okay, the ordering of the pointers matters to this function. If we calculate it in the prologue, it must matter to this function. And now there's no more danger. Yes, we're doing that same calculation in the function. But here, this is perfectly discernible because we said that the result of that comparison is part of the gross input. And now the result only depends on the gross input. And I know that one's kind of a deep dive. But that's really the procedural analog of the basic rule of functional programming, which is that you can call the same function twice and get the same result. Here, we always have this extra data hanging around. There's always addresses and padding bytes and representations. There's always stuff we need to ignore. The important thing is just remember to say what you need to ignore. And with that, I'm going to get to the wrap-up. Any questions before the wrap-up? Want to see the wrap-up? Here, the basic interface. So, the basic interface starts in the prologue. We claim that all of our parameters are proper. Then we have our implementation, and if the implementation returns, all the parameters have to be proper. The result, if there is one, has to be proper. Not if they are declared improper. We have that out, but most of the time. The result, if it's an object type, has to be destructible. If there's an exception, the parameters need to be proper. The exception needs to be proper. The exception needs to be destructible. Again, there's an out for improper parameters. There's no out. I don't see any reason to allow improper exceptions. They just cause trouble. Inside the implementation, only locally readable, writable, and destructibles are read, written, or destroyed, respectively. More generally, the implementation only uses doesn't use any capabilities that are held back by the caller. If the implementation wants a capability, it has to ask. At the end of the regular epilogue only, there's no irresponsible indiscernibility. That's the repeatability of the function call. That is, things that can't be repeated have to be indiscernible. At the end of both the regular epilogue and the exceptional epilogue, no leaked capabilities. We keep our capabilities in play until they are destroyed. Destruction recycles them into some other form. And finally, at the points where responsibility for behavior changes hands, there's been no undefined behavior so far. And that is what I know of the basic interface as of several months ago. I've been working a bit since then. But before we go on, basic interface for a member function. Very similar, except proper for star this on entry, proper for star this on return, proper for star this on exception when it's not declared improper. So not much different there. Basic interface for constructors. Very similar, except for how it handles star this. Star this goes from unoccupied space on entry to destructible and proper on exit, or still unoccupied space if there's an exception. And finally, basic interface for destructors. Star this is proper on entry and unoccupied space on exit either way. So, that's the basic interface. As I know it so far, a little incomplete still, I'm sure. There are a lot of questions left. I'm not sure I expect you to answer these questions. I don't know how to answer all of these questions. But there are a lot of things left unanswered here. Propriety for compound types, how do you do byte-wise copying? We touched on that a little earlier. We know some of the deal with padding bytes. Incomplete types and polymorphic and virtual functions, those get tricky. And interfaces for new and delete expressions, or really we need interfaces for all the built-in operators to make this work. So there's a lot of work there in just going through all the built-in operators and figuring out what their interfaces is. What is the interface for assignment or for a shift operator or for plus? Or for new and delete. And we have that, we actually did touch on, a bit on repeatability of function calls. We didn't touch on elimination of function calls. When can you say, I don't need to call that function at all, even though the call is in the code? That would be a really nice optimization to make. And we don't quite know when you can do that from what I've said so far. So those are lots of areas for future work. And now we can ask if there are questions. I do have one note. There's now a paper about this. It's in the ISO C++ Future Proposals Forum. You can search for procedural function interfaces. Earlier today, somebody Googled that, and it's pretty high on the list. It'll be on the front page for Google if you get there quick. But in any case, ISO C++ Future Proposals Forum. Any questions? Yes?
Looked at the contracts proposal that came out of Jacksonville.
The question is, have I looked at the contracts proposal that came out of Jacksonville? And the answer is yes. It's what to say about the contracts proposal. It's very functional in nature. And I don't think with an expression-based, non-procedural way of doing interfaces, we can get to where I want to go. Because I want to go to proofs, and I want to go to proofs for procedural code, not functional code. If you try to write code that is provable with expression-based interfaces, where every claim is just an expression and you can't put them in if statements and loops and so forth, you end up having to write your program in an entirely functional manner, has been my experience. So it doesn't get to where I want to go. That doesn't mean it doesn't get to someplace useful, but not where I want to go. Yes?
You didn't show any control flow in the epilogue. Is that something you want to see possible?
Yes, the question or statement is I didn't show any control flow in the epilogue. That's just chance. There is no reason to not have control flow in any of these places. Another thing that people ask about is, what about side effects in the prologue and epilogue? And my answer is, we're in a procedural language, there are going to be side effects. There are always side effects. Some electron got shifted from here to here and it has a different spin or something. There are always side effects. The important thing is not to eliminate side effects. The important thing is to know which side effects are indiscernible. Yes?
And what about similarly early return?
The question is, what about similarly early return? So if you look at the proposal, the return statement actually gets a little more complicated in interfaces. It's okay, it is just fine by me if you return from the prologue. You can return a value from the prologue, no problem. The implementation neighborhood never takes responsibility at that point. The caller just sees what goes on in the prologue, and there is no implementation neighborhood. Return in the epilogue is a little different because there's already a result. If the function has a result, it has a non-void result type. The result already exists in the epilogue. So you can use a return statement without an expression to return the existing result. And that's just fine too. It's just flow of control. If we're gonna reason about procedural programs, we're gonna reason about flow of control. Yes?
Was any of this work inspired by Pony?
Was any of this work inspired by Pony? I don't think so, because I don't know what you mean by Pony.
That's a programming language.
So, no. Anything else? Yes.
Is there a beginning of a library or some?
Is there a beginning of a library or?
There's a paper, but,
There's a paper. That is how things begin. And in some ways, it's just the beginning of a paper too. It's going to have revisions. Well, unless people utterly hate it, it's going to have revisions. And I guess I can. Yeah, there's a noise over there, but there. I told you you wouldn't be able to see properly if you sat on that side of the room. I think there is one more thing I want to say about flow control in prologues and epilogues, which is loops. I want to mention loops. Loops are really important. If I say that a vector is proper, I actually mean all of its elements are going to be proper. I also mean, by the way, that the addresses of the elements are going to be indiscernible. The address of the vector itself will be indiscernible. The capacity of the vector is probably going to be indiscernible in a const vector. Not quite sure about that last one. But in order to say all the elements are proper, you need a loop. And once you have loops, you can just say, yeah, loop from here to here, everything's proper. And in a slide we all saw this morning in Bjarne's talk, there was a little comment that said, you can't test reachability. Reachability is just a loop. You can run the loop, you can test it. It's not a very good test because undefined behavior is the result you get when the test fails, but it's executable code. You can test it. Did you have something? No. Anything? Yes?
I'll posit that you can't test reachability in single pass ranges because after testing reachability, you've disposed of the contents of the range, so you can't then process them in.
Yes. The point is that you can't test reachability in single pass ranges, say for an input or output iterator. And yes and no, you can test it, it's just the range is not very useful after you test it. So yeah, input and output iterators have this weird one-pass behavior that you can't repeat what's going on. And really, the answer for input and output iterators, I think, is mostly to put those things in inline. If you need to say this is what's going to happen, put it in an inline function. An inline function can act as an interface where the implementation is never reached. It just says what it does. So if you want to copy from input iterators, you can just say, here is what that means in an inline function. and not have to split things out into a separate interface and implementation. Because some things you can really only say once. Anything else? Yes?
The first part of the presentation, there was a puzzle at some point which I lost track and didn't see it again in the wrap-up. What was it?
So the point is there was a posit that he saw early that he didn't see in the wrap-up, and I will back up to it because the one posit I've put in this talk, and it's not perfectly a posit, something a little more complicated is going on here. But it is that the first place we ever see destructibility is here in the regular epilogue of a constructor. And this doesn't come from previous destructibility. It is created out of thin air. Yes?
Don't we have the same posit in the destructor?
The question is, don't we have the same posit in the destructor? And we do have the same fudge in the destructor, but in the destructor, it's actually a claim. That is, the destructibility, for the end of the constructor, you don't have to prove destructibility at the end of your constructor. It just happens. But in order to enter a destructor, you have to prove destructibility. That is, you have to use up that destructibility that you got from the constructor.
No, I mean the unoccupied space.
The unoccupied space. That's... Okay. The exact mechanism here, still a little fuzzy, still working on it, is... You know, I'm going to say you're right, that if I'm going to say that the thing that happened in the constructor was a posit of destructibility, I should be saying that the unoccupied space is posited at the end of the destructor. And the reason... What? Oh, sorry.
It's more symmetric that way.
It is more symmetric that way. The answer really is that I have an idea, I have a more solid idea, when I wrote these slides at least, of what unoccupied space means. And I think unoccupied space means I loop over this to cast this to unsigned char star plus size, and each individual byte is unoccupied space. And unoccupied space for a byte appears to be approximately the same thing as a proper byte. So you could actually prove that the things are unoccupied space just by looking at what all the individual part destructors did, maybe, but really I shouldn't have written it that way. And that kind of gets down to that posit really not quite a posit. And that one claim, those two claims, not quite right. Anyway, the session appears to be over, so thank you all for coming, and I hope you'll read the paper.